live on YouTube.
Okay, should I start?
Yes, please.
I believe that is your cue to start. Yes.
Okay, so thank you. So the title of this work is Improved Linear Approximations to ARX Ciphers and Attacks Against Chacha. My name is Murilo Coutinho. This is a joint work with Sousa Neto. We work at the Research and Development Center for Communication Security in Brazil. And this work, we present a new technique to find better linear approximations to ARX primitives. And using the proposed technique, we improve attacks against the stream cipher Chacha. So ARX stands for addition rotation XOR, and is a set of operations that is heavily used in the many symmetric primitives, such as the stream cipher Chacha. This slide represents the quarter-round function of the stream cipher. So as a summary of the attacks, we improved the attacks against 6 rounds of Chacha substantially, and also present a differential linear distinguisher for 7 rounds of Chacha, which you can see that reduces the time complexity, but has a trade-off with data complexity. So to give you a taste of what this is about, previous works showed Hurry and Mitra developed a theory for selecting combinations of specific bits to give linear approximations for Chacha. And as expected, the difficult part is to deal with the addition, which is the nonlinear operation for ARX algorithms. Thus, let us define theta of x and y as the carry function for the sum x plus y, and define theta I as the if bit of theta. So using some properties of the carry function, it's possible to obtain linear approximations for the quarter-round function of Chacha. In previous works, authors using the following result, which says that the if bit of the carry function can be approximated by y underscore I minus 1 with correlation a half. So with this equation, authors concentrated and find approximations for 1 round, and then repeating the same equations to expanding to further rounds. However, we can create a strategy to improve linear approximations when considering more rounds by combining with the following approximation for theta, which says that the XOR of 2 adjacent bits of the carry function cancel out each other with correlation a half. So for example, consider the word xb of the quarter-round function. So we can show that the if bit of the word xb has this expression here, which has a linear term XOR a nonlinear term in terms of the carry function. Then if we, for example, let's say that we want to find an approximation to the XOR of the bits 6 and 7 of xb. So in previous work, we would independently expand each bit, which would lead to this linear approximation below here, which with correlation a quarter. Instead, we can use this second approximation that we are proposing. And in this case, it's very easy to see that we can cancel out these 2 nonlinear terms right here. And we get this linear expression that not only has higher correlation of a half, but it also has fewer terms, which is good when we're trying to expand it further. So why it is useful against ARX cipher? Because it's possible to reduce the complexity in several cases. So let's consider the example of the addition of z equals to x plus y. So Suppose we want to find a linear approximation for the bit Z7, but we want to approximation for 2 rounds instead of 1 round. So in the first round, we can use the previous works to find approximation to Z7, which will be something like X7, XOR Y7, XOR Y6 with correlation 1/2. But now, for the second round, since the XOR operation will not change the indexes, and the rotation will probably keep Y6 and Y7 adjacent, then we can use the second approximation of the carry function to cancel out the nonlinear terms instead of expanding them, leading to a linear approximation with higher correlation and fewer terms to be expanded further. So using this technique, we presented the first explicitly derived linear approximation ranging three complete rounds of Chacha with correlation 2 to the power of -8. This is the expression, and also for 4 complete rounds. This is the expression, it's a very beautiful expression, and we proved this result in our work, and also we had computational results to check the results. So using also differential correlation from previous works, we improved the distinguishers, as we said before, for 6 and 7 rounds. So conclusions, we presented a new technique to find the linear approximations for ARX primitives. And using the proposed technique, we improve attacks against the stream cipher Chacha. And with these results, we expect that proposed techniques can be used to improve attacks against similar ARC-based designs, such as the stream cipher Salsa and the hash function Blake. So thank you very much. These are some references here, and I'm happy to answer your questions.
Thank you, Mario. I have the first question. Can you hear me?
Yes, I can hear you.
Are there any questions from the audience?
It's very, very bad, the audio.
Yeah, there's a horrible echo.
Is this better?
Yes, a little bit.
Any questions from the audience? Okay, then I have a question. As you might know, it was said in the morning, this is the Eurogrid with the largest percentage of students so far. So do you have maybe any advice for them? Because they'd like to improve your results here on the cipher. In which direction should they go to improve the results?
Against Chacha, this is a very good question. I mean, in our work, we showed that it's possible to find better linear approximations, but we couldn't combine with a better differential trail. So it may be possible to use the same technique to improve results. But yeah, that may be some new ideas as well.
Thanks. So let's move on to the second talk. Second talk is rotational cryptanalysis from a differential linear perspective. Practical distinguishers for reduced round. This is feet, Sulu, and Alzet. And the talk will be given by Hugo.
So the chair is aware Yunwen was having some audio issues earlier, so we may want to move on and come back because I also don't see them in the room anymore.
Okay, so keep everybody excited for this one. And move on to all of that research of needed a little preimage attacks on AES like hashing. Jump up. Floor is first.
Hi everyone. The work is on automatic search of meeting the middle pre-image attacks on AES AES-like hashing, it is drawn to work with 小杨、建、征、单平、思维、小云, and 真真. The target is focused on hash functions that use compression functions built from block ciphers, applying, for example, the secure PJV modes. The underlying block ciphers are AES-like, whose state is a two-dimensional array of cells. Each round function consists of 4 cell-oriented operations. The focused attack is the meet-in-the-middle preimage attack. The basic idea is to find ways to split the cipher into 2 computational chunks. Each chunk involves at least 1 message word such that it can be computed over values of the involved message word independently from the message word involved in the other chunk. Those message words are called neutral words. The 2 chunks are computed independently, but end up at a common state where their results can be pairwise matched. Several advanced techniques have been proposed to find better chunk separations and to cover more rounds. For example, the split and cut, the initial structure, the partial indirect matching. Suppose the number of possible values for forward and backward neutral words are 2 to the D1, D2, and the partial matching provide an M-bit filter. Then the attack complexity is about 2 to the N minus the minimum of D1, D2, and M. In 2011, the meet-in-the-middle preimage attack was applied to AES hashing mode with the initial structure and the partial matching through mixed columns. The attack successfully penetrated 7 rounds of AES. In the attack, the neutral word are directly selected from the encryption state, while the key states are fixed. In 2019, it is shown that introducing neutral words in the key state is feasible and can provide more degree of freedom and help to cancel impacts. However, due to the limitation of manual analysis, the considered configurations are quite limited. Actually, there are many choices of starting and matching point, choices of neutral bytes, and ways of cancellation of impact, such that manual analysis inevitably misses many possible attacks, hence cannot ensure optimal results. This work generalized the meet-in-the-middle attack by removing many previous limitations and systematically searching an extended attack space. The search covered all possible combinations of starting and matching point, both in encryption and the key schedule. It allowed to select neutral bytes for both chunks from both encryption and key state. It allowed to consume degrees of freedom to cancel impact on any possible runs. We formalized the attack configuration using explicit defined rules, including how the attribute of cells propagates through various round operations and how to do partial matching. We then translate the formalized attack configuration into mixed integer linear programming models, reduce the searching for the best attack into solving optimization problems under constraints in MLP. The attribute of each cell of each state is encoded using binary variables, indicating whether the cell is computable for each chunk. Initial degree of freedom are defined according to the attribute of cells in the selected starting state. The rules on how attributes are propagated through each round operation are translated into linear inequalities. Additional binary variables are introduced to indicate the conditions of case-by-case rules. After defining these indicator variables, the attribute propagation through the operation can be constrained using these indicator variables following a case-by-case analysis. The number of consumed degrees of freedom is also counted. The most involved one is the XOR MC rule for the backward chunk, which is shown to be necessary to cover more possible ways to cancellation of impact. The matching rules are translated to count the degree of match, the initial degree of freedom, and the cumulated degrees of consumed degrees of freedom are used to compute the final degree of freedom. And the objective function is defined to maximize the computational advantage. The generated MLP models are then solved using a solver Groovy. It turned out to be very efficient to perform exhaustive search for various instances of AES hashing mode and AES-like hash functions that include an attack on 8-round AES 128 hashing modes, which is experimentally verified, and the full round of Harika 512 V2. That's all. Thanks for your attention.
Thank you, Junjun.
Thank you.
Yeah. So any questions from the audience? I'm also checking the Zulip, where people can also post questions. Mostly cricket so far, also for the previous sessions. Okay, Junjun, in that case, I have a question for you. I think it's really exciting to see so many papers using automated techniques. In this case, you were using mixed integer linear programming. Did you consider using other types of automated techniques as well? Like why specifically mixed integer linear programming, not like set solver, for example, or a different method?
We think the direct truth is mixed integer linear programming, and it currently is very efficient. So we haven't used others, so it's already enough. Yes.
Okay. So you didn't try a set solver because it was fast enough? Just
it's
use
already efficient.
Yeah. Okay, great. Let's thank Junjun again.
And please excuse me for interrupting. We have a request to deal with technical issues real quick.
So you can hear us now?
Yes, it seems to work better now.
Okay, what about now? Do you still hear us?
Yes,
Do you hear me scratching the microphone?
yes.
Okay, let's try, go there and speak.
Thanks, everyone. We will continue in a moment.
Speak.
Excuse me, can you hear me?
Yes.
Can you?
Let's move to the previous talk then. I see everyone is.
Oh, that's terrible. That's terrible audio.
Okay, that's not the one.
Hello.
Yeah, that's better.
Okay. Okay, I would suggest we move to the previous talk. Seems that Yunwan is now connected. So the talk is titled Rotational Cryptanalysis from a Differential Linear Perspective. Yunwan, the floor is yours.
Okay, can you hear me?
Yes.
We can.
Okay, you're good. Let me share the screen. Okay, can you see my screen now?
Yes, we can. And you'll just need to hit.
Okay.
You'll just need to go into play or
yes,
presentation.
I need to. And, okay. Okay. Yes. Okay. Thank you. Okay. Good evening, everyone. I am Yuman, and this is a work, rotational analysis in a differential linear perspective. It is a joint work with Siwei Sun and Charlie. In this study, our focus is on differential linear analysis, and we are interested in two questions. how to extend the framework of differential analysis and how to compute the differential linear probability with improved accuracy. So what we do in this paper is to generalize the differential. So we propose
I believe Yunwen is having connection issues now. So
I think we have to move to the next talk.
Okay, let's move to the next talk. So the next talk is titled "A Deeper Look at Machine." Yeah, I'm not on mute. Okay, a deeper look at machine learning-based cryptanalysis, and will be given by Adrien Benamira. Adrien, the floor is yours.
Okay, thank you very much. Can you hear me?
We can hear you perfectly.
Perfect. Okay, so my connection of internet is also unstable, so I hope we will have no trouble. Hello, everyone. Welcome at this presentation entitled "A Deeper Look at Machine Learning-Based Cryptanalysis." So my name is Adrien Benamira, and this is a joint work with David Giraud, Thomas Perrin, Chuan Tan. So there are three parts in this presentation. The first one introduces the 2019 crypto paper of Aaron Gore. Then we will explore the intuition of Gore neural distinguisher with two perspectives, cryptanalysis and machine learning. So in Crypto 2019, Aaron Gore introduced a neural network-based distinguisher, neural distinguisher, ND. He applied it on reduced rounds of spec. The binary classification task learned by the neural network is the following. The input is a pair of binary ciphertext, and the neural network predicts if the input comes from a fixed input difference plaintext or from a random input difference plaintext. So this neural network performs better compared to pure differential distinguishers. One notable result from Gore's paper is that he improved the 11-round key recovery attack. So these are the results for the Gore neural distinguisher compared to purely distinguishers. So we can observe that every time the neural distinguisher is better than pure differential distinguisher. So that means that the neural network is able to learn a property P that we don't know and that we want to approximate, sorry. And this is what we are going to see that we have done in our paper. So can we replicate the results of the neural distinguisher without the neural network?
Can you speak a bit louder or move closer to the microphone?
Sorry. Okay, I will speak louder. Okay, so first part, cryptanalysis perspective. Is it better like this? Hello?
yes, we can hear you a little bit better, I think.
Okay. So we introduced the average key rank distinguisher. The idea is that we make use of the mask DDT, that is a DDT with some position ignored at n-1 round for n round distinguisher. Then we decrypt the last round with all possible subkeys and take the average probability. Depending on the average probability, we put 1, real, or random, 0. Note that this distinguisher is crafted such that the data and time complexities match that of Gore neural distinguisher. These are the results of our average key rank distinguisher compared to Gore neural distinguisher. We would like to especially highlight that first, every time we match the accuracy of the neural distinguisher, and also we have the same conclusion with the neural distinguisher for 97.6% of the test set. So now the machine learning perspective. So the neural distinguisher can be modeled into 3 blocks. So here you have the overall architecture. Here you have the inputs. And the first block, which is a 1D CNN with a kernel size 1, transform the input. Then you have 10 layers of 1D CNN. And at the end, you have a filters F. which is a flatten, which is where each element is a nonlinear function over the inputs. Then you have finally a multi-layer perceptron to map to the output. So our objective here is now to replace each of these individual blocks. So we start from the inputs. Then we have delta L, delta V, V0, V1, which correspond to the output of the first block. So this is the input transformation. Then from the neural distinguisher, we extract a mask. And this mask, we apply it over the inputs with an AND operation. Then we compute a DDT. We call this DDT mask ODT because we don't compute on differential, but on the output of the cipher, and we apply a mask. Then at inference time, we compute the probability of having real, means having one, knowing the input and the mask one. Of course, we can repeat this operation for multiple masks. So all these probabilities, we consider that this is the approximation for the nonlinear, for the features F above. And then we finally classify with any ensemble classifier. So just a big picture of that, that means that you can replace the ResNet by multiples DDT, actually multiples mask DDT. And this pipeline actually gives pretty relevant results compared to the neural distinguisher. So here you have the results on 5 rounds, and here on 6 rounds. The matching is also pretty high. We have also observed that it can be extrapolated to 8-round Simon. Thank you very much for your attention. Do you have any question? So I will handle the machine learning part, and Chuan will handle the cryptanalysis part.
Thank you, Adrien. So, I mean, you figured out by now, I have a question if the audience doesn't have a question, but don't rely on me for everything here, right? Questions from the audience, please. Anyone? Yes. Can you state your name and ask your question?
Hello, can you hear me? Okay, good. Hi, I'm Fernando. Thank you for the presentation. I was wondering, in the abstract of the paper, you mentioned that the distinguisher somehow learned the differential table inside the cipher that the Crypto 19 paper was attacking. Do you have any insight if it is because learning this table is essentially equivalent to training a neural network? Like, is there a clear mathematical relation there, or is it just that it happened to do it?
Okay, so I will answer it for the machine learning perspective, and maybe I will let Chuan add a word if he had something to add. So no, there is no clear mathematical proof that you can replace that the neural network is learning a DDT. So I want to be clear, we don't have any mathematical proof for the moment, actually, maybe later. But and moreover, maybe I was not clear enough, but the DDT is only, actually it's multiple DDT and multiple mask DDT, and it's only on the convolutional part. So it's not the all blocks. So I divided the neural network into 3 blocks. Here we are only talking about the block number 2. And yeah, for the moment, that's all. Maybe Chuan have something to add. I don't know.
Thank you. Does that answer your question, more or less, or?
Yeah, I guess it's not clear, which is perfectly fine. Thank you.
Okay, it's allowed to ask more than one question if somebody else has a question in the audience. No? Okay, in that case, I would propose that we move on to the next talk. Next talk is entitled 3 third-generation attacks on the format-preserving encryption scheme FF3. And the talk will be given by Ohad Amon. Ohad, the floor is yours.
Okay. Can you hear me?
Yes, we can.
Okay. I'll be there. So the paper I'll be presenting is 3 third-generation attacks on the format-preserving encryption FF3. This paper is a work by myself, or Dunkelman, Nathan Keller, Yalonen, and Adishami. So the cipher that we are attacking is FF3, which is a format-preserving encryption scheme, or FPE. The special thing about an FPE is that it's a symmetric cipher that can encrypt any domain into itself, unlike most symmetric ciphers that can only work over a specific domain. For example, using an FPE, we can encrypt the credit card number such that the ciphertext is also a valid credit card number. This is useful mainly for encrypting legacy databases whose formats cannot be altered, or communication packets where the data needs to follow a specific format. So how does the cipher look? FF3 is a Feistel construction that accepts plaintext of a domain M on N, along with the key K and a tweak T, and it encrypts them to ciphertext into the same domain. The tweak acts as an IV in order to enable independent encryptions of the same value. Throughout our work, we assume for simplicity that M equals N, and therefore we use N to express complexity, which is expressed using data, time, and memory. Note that FF3 and format-preserving encryptions in general are generally used on relatively small domains, meaning that heavy usage of time and memory in relation to the domain size is practical. In that case, we generally prioritize minimizing the data requirements of attack, even at the expense of additional time and memory. So let's show previous attacks against FF3. The purpose of all of these attacks is to enable encryption and decryption of all plaintext and ciphertext under a certain tweak. The most trivial way to do this is simply full codebook recovery. That means that assuming we have access to an encryption oracle, we can query that oracle on all possible plaintext and then keep a table of size n squared that holds all of the ciphertext. The first improvement to this attack was the first generation attack by Dirac and Vadonnet, which meant that we now no longer need to query the entire domain, and we can now recover all plaintext and ciphertext at a heavy additional cost in time. The second generation attack by Huang, Miller, and True in 2019 improved upon this by keeping the same data requirements while significantly reducing memory. We present 3 additional attacks beyond this. First, we have a symmetric slide and an asymmetric slide attack. These follow the footsteps of the second generation attack by Huang, Miller, and True by significantly reducing the data requirements while also decreasing the time and memory requirements, also adding a better time data trade-off, meaning now we can reduce the data from n to the power of 11/6, which is what we got in the second generation attack, to up to n to the power of 3/2, which is a significant increase. Furthermore, we present a third attack, a cycle detection slide, which is a practical application of an attack previously shown by BM Dunkelman and Keller in 2007, which was then considered impractical due to high domain sizes of ciphers. Since FF3 works over low domain sizes, that means that this attack, which was previously considered theoretical, is now practical on FF3, and we also verified it in our paper. Furthermore, this attack makes interesting use of the structure of permutation graphs. So this is the attack we present in our pre-recorded talk, since it is also the most interesting. All of our 3 attacks follow the same similar attack outline. First, we create a reduction from 8-round FF3 to 4-round FF3 using a slide attack. Second, we break 4-round FF3 by reconstructing the codebooks of each of the individual RAM functions using a subroutine known as PRF reconstruction, which is based on a similar subroutine presented by Huang et al. And then we can combine the above 2 in order to reconstruct the full FF3, which is 8 rounds. Further contributions that we give in our paper beyond these 3 slide attacks are, first, we also improve the time complexity of PRF reconstruction itself, where Huang et al. Gave us n to the power of 5/3, and we improved that to n to the power of 3/2. And also we introduced 2 related domain attacks, which are attacks that require querying over separate domains. The first is a generic attack on cycle walking FPE schemes, and the second is a distinguishing attack on FF3 and FF3-1. And we also have some additional minor results that I don't really have time to go over now. So to conclude, presented these 3 new attacks on FF3, where the first 2 significantly reduce the data complexity while also improving the time and memory beyond what was known earlier. And the cycle detection slide is a practical application of an attack previously thought to be theoretical. Any questions?
Thank you, Ohad. Yeah, really interesting talk. Format preserving encryption is one of the things on my plate at NIST and X9 standardization. So I have a lot of questions, but I see we have a question from the audience as well. Go ahead. Please state your name and ask your question.
Hi, I'm Simon. I have a question whether this is specific to the format preserving. Like, is there anything specific to the format preserving property, or could it also be applied the attack to format transforming encryption?
I'm not really familiar with format transforming encryptions, but these attacks aren't general against any FPEs. They rely on a specific weakness that FF3 has in its tweak structure. So it cannot be generalized to other ciphers.
Okay, thank you.
So a question that I have is, as you might know, there's a proposed update for FF3 that is called FF3.1 or FF3-1, depending on the standard that you're looking at, where the proposal is to set a few bits of the tweak to 0. Actually, a suggestion by Serge Faudenet in his paper with Betül Durac. Have you looked at differences between FF3, FF3-1 or .1, and if there might be some idea of perhaps extending some of the results that you have here?
FF3.1, our attacks, it does invalidate our attacks since the weakness relies on basically making encrypting under 2 separate tweaks that generate similarities between the rand functions. So those are invalidated by that fix. However, we do present one of our related domain attacks does address FF3.1. Our main 3 slide attacks that are the main part of a paper, however, are not relevant for FF3.1 since it fixes the issue with the tweak structure.
Okay, thanks. I hope that some of the students maybe in the audience can say, I can prove you wrong and I have an attack for that cipher as well. So that's a challenge. Let's move on to the next talk, cryptanalysis of the GPRS encryption algorithms GEA1 and GEA2. And the talk will be given by Christophe Bayerle. Christophe, the floor is yours.
Can you hear me?
Yes.
Yes. Thank you very much for the introduction. This talk is about the stream ciphers GEA1 and GEA2. Those are proprietary stream ciphers for encrypting the GPRS traffic in the early 2000s. And so compared to the A5 algorithms, which were used for voice encryption, these algorithms were used for the data encryption in the 2G standard. And they were designed by ETSI, which is the European Specification Organization, in 1998. There were some reports on the insecurity of GEA1. So the ETSI already prohibited the implementation of GEA1 in 2013, while GEA2 is still mandatory to be implemented today. But still, both algorithms are not yet disclosed or publicly analyzed. So if you quote from an official design document by ETSI from 1998, it says that the algorithm should be generally exportable, taking into account current export restrictions. And that within this operational context, the algorithm provides an adequate level of security against eavesdropping. Yeah, so the question remains, what are these official restrictions for fulfilling this export conditions? And they are not explicitly stated, but if you look at some other sources from that time, for example, some French laws, there is a strong indication that this is associated to 40 bits of security. Yeah, so we expect that this algorithm has a significant weakness, although it has a 64-bit key. Yeah, so we would expect some security around 40 bits. In this talk, I only focus on the cryptanalysis or on the weakness on GEA1. For the full details also about GEA2, I refer to the paper or to the longer talk. Yeah, so GEA1 is a stream cipher which operates on a 96-bit internal state. So this is depicted by these 3 registers here, where each blue cell indicates 1 bit. And from the session key and from the IV, there will be a 64-bit seed generated. Yeah, from this seed, you can recover the session key. And then there is a linear operation which maps the 64-bit state, the 64-bit seed to a 96-bit state. And then the states generate 1,600 bytes of key stream by clocking the LFSRs and then choosing from each register 7 bits, which go into this function f. And then the 3 bits are XORed to generate the bit of the output stream. And the goal of the attacker is to recover the 64-bit seed from some bits of known key stream ZI, where this data is limited by the available data per frame, which is 12,800 bits or 1,600 bytes. So the weakness here is that after the linear initialization process, the joint initial 64-bit states of the 2 registers A and C is only in a set of 2 to the 40 possible states. Yeah? So we would expect an entropy of 64 bits for registers AC, but in fact it is only 40 bits. And this would directly lead to a very simple meet in the middle attack, where the idea is that you generate a table for all 2 to the 33 possible values for register B, and store the output stream after the function f. Yeah? So this BI values in a sorted table, and then you exhaustively search over the 2 to the 40 possible states for A and C, and find a match in the table. Yeah? And this gives an attack of time complexity 2 to the 40, and only needs 65 bits of known key stream. Yeah, but it needs some memory complexity because you have to pre-compute this table. It's roughly 45 GB of memory complexity. Yeah, so we have seen that here there is an attack which matches this 40-bit security. We analyzed whether this attack is likely to occur by chance or if it's really an exceptional property. So the weakness was that the image of the joint initialization matrix for these 2 registers has a very low dimension. Yeah? Here dimension 40. So we experimentally checked what would happen for 2 random primitive LFSRs. Yeah? So we took the exact initialization process as for GEA1, but we used random feedback polynomials. And from our experiments, we extrapolate a probability of 2 to the minus 47 to obtain this weakness by chance. Yeah, so it is really an indication that this was deliberately weakened to fulfill these export restrictions. I will conclude the talk by talking about implications on the security today. So we were really surprised when we found out that the most modern smartphones still supported GEA1, although it was already forbidden to be implemented in 2013. Almost all of the phones we tested had this GEA1 support. Yeah, so we made a responsible disclosure before we published our attacks. So we went to GSMA, which is the organization of all mobile network operators, and also to ETSI, and yeah, participated in this vulnerability disclosure program, with the goal that now GEA1 is disabled in most devices. Yeah? So there were security patches that got rid of the GEA1. And in the long term, GEA2 will also be forbidden in new releases. Yeah? And right now it is discouraged to be implemented. Yeah? So to conclude, GEA1 offers only 40-bit out of 64-bit security, which needs a memory of 45 GB and only 65-bit of known key stream. We also analyzed GEA2, and we found out that it is less weak, but still breakable. In particular, we presented an attack with time complexity of 2 to the 45 GEA2 evaluations, but it requires almost all of the available key stream per frame. And because we have seen these algorithms still implemented in modern forms, this insecurity has affected our communication until today. Thank you very much for the attention, and I'm happy to take the questions.
Applause for Christoph. Any questions for Christoph from the audience here? Yes. Yeah, it's a long press to activate the microphone. It might be on already. Yeah.
Hi, thank you for the talk. I was wondering, you mentioned in the first slide that ETSI at some point prohibits implementation of GEA1 in devices. Did they give any specific motivation about this?
As far as I remember, I think it was because of these weaknesses by Noel et al., which were found in 2011. Yeah, so there were already some claims about the insecurity. So ETSI decided to forbid the implementation of GA1.
Makes sense. Do you think something like that is going to now happen for GA2?
Yes, I think so as well. Yeah.
Thank you very much.
Thanks. I have a question about the responsible disclosure process that you went through. Can you tell us a bit more about how that went and how quick or how long and frustrating the process was, what your experiences were?
Okay, so David Rupprecht, our co-author, completely handled this.
Yes, I'm here.
I cannot, yeah, he's here, yeah, so he can answer this.
So hi, we did two responsible disclosures, one with the GSMA and one with the ETSI. The main aim of the GSMA responsible disclosure was basically to disable GA1 in the current phones. Basically, we needed to inform all baseband vendors and mobile network, mobile operators, mobile phone vendors, and operating suppliers. And the other aim for the ETSI responsible disclosure was basically to let them know that GA2 is also kind of weak. So regarding the ETSI, we can make it short. They acknowledged our findings and also the reception of our paper first, and then also the findings, but there were no big communication involved. The main
How much time did it, sorry to interrupt, how much time did it take for them to acknowledge the findings?
I think got the first response within 7 days and like roughly 1 month that they respond after requesting what their plan is to deal with the whole thing. But it was not fast, but also not that didn't take that long. So
they confirmed in 7 days that the vulnerability was correct.
No, they were just confirming that they received the paper, so our submission. They never confirmed on the vulnerability.
Sounds like a familiar story.
Yeah. So they never, to make this clear, they never confirmed on the vulnerability itself. So that's it. The main responsible disclosure was with the GSMA. So where that was a good cooperation where we got always an update who is currently involved in patching which with which party and all this kind of stuff. They were really keen to get rid of GA1 from the phones. So that's it. Yeah.
Great, thanks for an interesting result. Thanks for practically relevant cryptanalysis results. We're now going to try again. Yunwen says that she feels confident that maybe this time it will work. To launch the session, to launch a talk on rotational cryptanalysis from a differential linear perspective. Yunwen, the floor is yours.
Okay, thank you. Can you hear me?
Yes.
Okay, let me try. Okay. Hello everyone. Sorry for the trouble previous. I am Yuman, and this is work rotational cryptanalysis in a differential linear perspective. And this is a joint work with Si Wei Sun and Chao Li. In this study, our focus is on differential linear cryptanalysis, and we are interested in two questions. How to extend the framework of differential linear cryptanalysis, and can we evaluate the differential linear correlation with improved accuracy? So what we do is to generalize the differential linear cryptanalysis by replacing the XOR difference with rotational difference. So we propose rotational differential linear cryptanalysis where giving a pair of rotationally related inputs X and X prime, we study the linear approximation with mask gamma on the output difference of Fx and Fx prime through the cipher. So and then we proposed three methods to compute the rotational differential linear probability. And the first approach follows the differential linear method of separating a cipher into two parts and find a good rotational differential and a good linear approximation to concatenate. And here we have a formula to compute the bias of the distinguisher. But to better characterize the dependency between the two parts, a link between the rotational differential and linear approximation is presented. And based on it, we extend a previous theoretical formula on differential linear to rotational differential linear as well. And this formula will require us to enumerate all possible intermediate linear masks to compute the exact probability. And next, we proposed a third approach to compute the rotational differential linear probability round by round. So first, we observed that the previous rotational distinguisher on K-check F was a special case of rotational differential linear where the output mask is 1 bit. And then our second observation is that the probability of the output bits being unequal through a Boolean function can be predicted by the following formula here. And our third observation is on the effect of the constant. So the constants into a permutation, it actually introduced a new rotational difference here. Like the constant C shifted XOR with the constant C. And these three observations, they allow us to compute the rotational differential linear probability by evaluating each round function. And next, we go one step further to extend a rotational differential linear cryptanalysis to ARX ciphers. So first, we like to mention that what works for rotational differential linear in our paper, also it works for differential linear. Just we set the rotational amount to be 0. And to get the propagation rule for modular addition, we found that the dependency in the carry function cannot be ignored. So we deduced a carry rule that takes the dependency into fully consideration. And based on the carry rule, we also have a modular addition rule for the differential linear propagation in a modular addition. And this is experimentally verified on a small scale modular addition. And this will help us to compute differential linear and rotational differential linear probability round by round. And the following is an overview of all the applications in our paper. And we found rotational differential linear distinguishers and differential linear distinguishers for 3 permutations, Fritz, Zulu, and RZ. And we tested the experimental probability to verify the distinguishers when the data complexity is possible. To conclude, we proposed rotational differential linear analysis as a generalization of differential linear analysis, and the theoretical analysis on rotational differential linear is given. And then a new method for computing the probability of rotational differential linear distinguisher is presented, which is efficient by evaluating round by round. And finally, our technique is applied to 3 permutations where practical distinguishers are obtained. Thank you very much for your attention, and thank you for your time.
Thank you, Yunwen. Question from the audience? No, I have a question, and this may be an obvious question. Have you tried, you can hear me, right?
Yes.
Yes. So I see you've applied your results to several ARX algorithms, including SIP-hash. Have you also looked at Chesky?
Yes, actually, I looked at Chesky. But for Chesky, I think the dependency is stronger than SIP-hash because SIP-hash has a wider block size.
Okay, so why not include a result on Chesky in the paper, or?
Because we actually we didn't improve the current distinguishers on Chesky, so
okay.
Yeah, so we didn't include that result.
Okay, thanks. Any questions from the audience still? No? Okay, then I'd like to thank all the speakers of this session. So we now have a coffee break, and we're going to